All right, let's talk about electricity. It's everywhere. It powers our entire world. But let's be honest, for most of us, it kind of feels like magic. Well, the goal here is to replace that feeling of magic with a really solid mental model. We're not going to get bogged down in a bunch of complex math, I promise. But by the end of this, you'll really get the logic behind how it all works.
I mean, just think about this little guy, your phone charger. It seems so simple, right? You plug it into the wall, connect your phone, and somehow your phone just comes back to life. But what's really going on inside this little plastic box? By the time we're done here, you're going to understand the core principles that make this whole thing possible. Okay, so first things first, we need to correct a super common misconception. If you ask most people, they'll say electricity is energy flowing through wires. And, they're not totally wrong, but it's an incomplete picture. It's missing the most important piece of the puzzle. The real story is about something much more fundamental.
And that fundamental thing is electric charge. That's the real star of the show. It's a basic property of matter, just like mass is. And this charge comes in two flavors. You've got positive and you've got negative. The way these little charges interact and, more importantly, move, that is the true story of electricity.
So inside every single atom, we've got these three main particles. But for our purposes today, we only really need to focus on one of them, the electron. See, the protons are locked into place inside the atom. They don't really go anywhere. But the electrons, especially in certain materials like metals, are free to roam around. They are the movers, the shakers, the workers of the electrical world.
And you've definitely experienced electric charge in action, even if you didn't realize it. You know that little shock you get when you touch a doorknob in the winter? Or how a balloon sticks to the wall after you rub it on your hair? Well, that's static electricity, and it's our first big clue about how charge actually behaves.
So what's actually happening there? It's pretty simple. As you shuffle your feet across a carpet, you're literally scraping electrons off the carpet and they're building up on you. So now you have a charge imbalance, too many negative electrons. And here's the thing, nature hates an imbalance. It always wants to get back to neutral. So the second you touch something like a metal doorknob, you give all those extra electrons a path to escape. And zap, that little spark you see and feel is just nature balancing its books.
Okay, so now let's figure out how to get that charge moving in a useful way. To do that, we gotta understand two absolutely critical ideas, voltage and current. And the best way, the classic way to think about this, is with a water pipe analogy. Voltage is like the water pressure in the pipe. It's the push. And current is the actual flow of the water. It's how much water is moving past a certain point. But that flow isn't always a free-for-all. What if our water pipe gets narrower in one spot? Or there's some gunk clogging it up? Well, that would slow down the flow of water, right? In electricity, we call that exact same idea resistance. It's basically anything that opposes or limits the flow of that current.
And this all boils down to a really simple, intuitive relationship. You don't need to know the formula for Ohm's law, just the logic. If you increase the push, the voltage, you're going to get more flow, more current. And if you increase the blockage, the resistance, you're going to get less flow. It's a perfect balancing act. It just makes sense.
Now, for any of this to actually do work, to light up a bulb or charge your phone, it needs one more thing, a complete, unbroken path. We call this an electrical circuit. Think of it like a racetrack for electrons. They have to have a path from the start, through whatever device they're powering, and all the way back to the beginning. If there's a break anywhere in that loop, everything just stops.
And that idea perfectly explains what a simple light switch does. It's not some kind of magical box. All it is a drawbridge on that electron racetrack. When you flip the switch on, you're lowering the bridge, which closes the loop and lets the electrons flow. Flip it off, you're raising the bridge, creating a gap that stops everything cold. Simple as that. Of course, not all materials are created equal when it comes to letting electrons move. Some materials, we call them conductors, think of metals like copper, are like wide open superhighways where electrons can just cruise along easily. Other materials, called insulators, like the rubber or plastic coating on a wire, are like giant brick walls. They stop electrons in their tracks. And we absolutely need both to control electricity and use it safely.
Okay, so this brings up a really important question. We know resistance is what limits the flow. So what would happen if we created a path for electricity that had almost no resistance at all? What happens when you remove the speed limit on that electron highway?
Well, that situation has a name. It's called a short circuit.
This is what happens when the current finds an accidental shortcut, a super easy path of low resistance that lets it bypass the thing it's supposed to be powering. It's an electrical highway with no rules and no speed limit.
And the results can be really, really dangerous. With resistance basically gone, the current just skyrockets to incredible levels. And all of those moving charges create friction, which generates a massive amount of energy as heat. This is exactly why short circuits can melt wires and are a huge fire hazard.
This brings us to another really important distinction, the difference between the electrons themselves and the energy they carry. Here's a great way to think about it. The electrons are like a fleet of tiny delivery trucks. They are just the carriers. The energy is the package they're delivering to your light bulb or your phone to do the work. The trucks themselves don't get used up. They just drop off their package and then loop back to the power source to pick up another one.
Now, those little delivery trucks can move in two different ways. The first is direct current, or DC. That's like a river, a nice, steady, one-way flow of electrons. This is what you get out of batteries. The other is alternating current, or AC, which is what comes from the outlets in your wall. This is less like a river and more like a frantic tug of war, where the electrons get pushed back and forth, delivering a little bit of energy with each wiggle. And here's a mind-bending fact that confuses a lot of people. The actual electrons themselves drift through a wire incredibly slowly. I mean, slower than a snail crawls. So how does a light turn on instantly when you flip the switch? Well, imagine a pipe that's completely packed full of marbles. If you push a new marble in one end, another one pops out the other end almost instantly, right? The push, the signal, travels at nearly the speed of light, even though each individual marble barely moved at all. It's the same with electrons.
So, let's put it all together into our new mental model. This is it. Electricity isn't some vague magical energy. It's the controlled movement of electric charge. Voltage is the push that gets it moving. Current is the actual flow of that charge. Resistance is the limiter on that flow. And a circuit is the required closed loop that makes the whole thing possible. This simple framework is the backbone of all electronics.
So now that you have this model, now that you see the rules of the game, I want you to look around. Look at your toaster, your laptop, the power lines outside. They all operate on these exact same fundamental principles. The magic hasn't gone away, but hopefully you now have the tools to really appreciate the incredible engineering that's hiding in plain sight all around you.